Hi, I'm Jack, and this is my Lab 3 report. General idea of this lab is to explore magnets and their properties. We can determine a magnet's dipole moment by solving for it in the magnetic field equation. We know B, the magnetic field, because we can measure it. So we use this kind of general equation, which uses some constant, which we will solve for, and a factor that changes as distance changes. So using algebra, we can solve for n, how it changes with distance, and then we can also solve for k eventually. So in short, I found mu of my magnet, the magnetic dipole moment, to be 0.0077 approximately. Here it is in my derived equation, and the distance factor n to be 3.86, which we know in the real equation is 3, so it's reasonable. This tells us that as magnets that as the magnet gets closer to what we're measuring, the magnetic field will increase, and as we get farther away, the field will approach zero. So I used fridge magnets stuck together just to get a stronger magnet. So to start the experiment, I rotated my phone until the x component was 0. This is important because it means when we're measuring in the x-axis, the Earth's magnetic field isn't interfering, which just makes our experiment simpler. So I used tape on the floor just to hold this rotation. So to set it up, first I had to find where the magnetometer was. So I put the magnet here and slid my phone up and down and found that it peaked right along the top of my screen. And I moved the magnet up here and slid the phone side to side, keeping that rotation. And it peaked right under the Wi-Fi symbol, so that tells me the magnetometer is right there. So then to get these measurements, I just kept the magnet in the x-axis and moved it until I got the value I wanted, so 20, 70, 120, 170, and 220, and then measured the distance there and found the averages in this chart here. So for the math, we know our general equation is this. We can take the log of both sides, and nicely enough, it gives us a linear equation. So n is the slope, a. We can find that with a regression, and the y-intercept is log of k. So we know how logs work, so we can solve for k. We know that k in an on-axis magnet is mu naught over 4 pi times 2 mu. So we can solve for mu, and then we can use those numbers to make our general equation, just like this. So in preparation for our computer model, we will also we'll find the off-axis case. So to do this, I did the same thing as the previous experiment. I just slid the phone up distance d so that we got a 45-degree angle. This gives us a magnetic field in the x and y directions. So we just take the x magnitude and the change in y magnitude and find the net there, and then we'll keep that number in mind for when we make the computer. So here's what my code does. We have 2 arrows for the on-axis case and 4 arrows for the off-axis case, all based on the center of the magnet here. And then the magenta line is the 45-degree case, which is just simulating what I did in the previous slide. The way the program works, we define the magnet's mu value, and then at each of these points, we find the location. We define the location, and then we call dipole B, and it calculates the magnetic field direction and magnitude at that point, and then we just display those as arrows with a scale factor so that it's reasonable. In the end, what this tells us, experimentally, I found n to be 3.86. We know in reality it's 3, but it's in the right realm, which I found for all these numbers. They're in the right realm. It's just inaccurate in a way. Experimentally, B at 45 degrees, which I truly measured, was 7e negative 5 Teslas, which we know that's just a fact because we can measure it. And the computer, based on the mu value I found, showed it should have been 1.9 e negative 6 Tesla, which means that my mu value wasn't exactly right, which is likely just because my measurements were inaccurate and my magnets were also really weird. Instead of being North Pole, South Pole on the ends like I expected, it turns out it was more like this corner was north, this corner was south. So as I rotated it, it would change the value, which is really weird. I had to keep that in mind, so I actually used tape to keep the rotation from changing. I just didn't show that in this picture. But it kind of raises a good question. If we stuck two magnets together, what would happen? Well, I would expect B to be double because there's double the magnet there. And so then at any point in space, the magnetic field would be twice as much. So, thank you for watching.